All right, good afternoon all, and welcome to our webinar that is hosted as part of the activities that are leading up to our SIMM Geometallurgy conference, focused on future-ready geometallurgy, which is taking place next week. And part of the lead up to the conference, we've had one webinar already, and this is our second webinar. And the aim of these webinars is to increase the exposure of geometallurgy to many of the SIMM members and people who are interested from the community in mineral processing. So we're very fortunate to have Associate Professor Mehdi Parian with us today, who is presenting all the way from Sweden. And I first met Mehdi probably about 10 years ago when I was visiting there, and have watched him in his own research career as he has developed and built his own niche in geometallurgy. So he is an associate professor at Luleå University of Technology, which is in northern Sweden, and his research focus is on ore characterization and comminution. The work integrates advanced imaging, machine learning, and innovative testing methods to maximize geometallurgical data on minimal samples. In this work, it has contributed to projects on automated ore texture classification, small-scale grindability testing, and the development of non-destructive and small sample techniques for early ore characterization. This research bridges mineralogy and texture, minerals engineering, and digital technologies to improve metallurgical forecasting and support geometallurgy. So Mehdi's going to run the webinar. If you have any questions, you can post them in the Q&A. And then when his presentation is finished, then we will deal with all the questions at the end and we'll go through them. But you can post the questions as you think of them, that's fine. So I'm going to hand over to Mehdi, and we're very grateful to have you with us today. Thank you.
Thanks, Megan, for the introduction. Good afternoon, everyone, and thank you for joining us. Today, I will share how we can maximize geometallurgical value from limited drill core material, from non-destructive measurement techniques, or the steps that we normally have to perform anyway. So little about Luleå and LTU, Luleå Technical University. For those who are not familiar with Luleå, it is a relatively small town city in the north of Sweden. Close to the Arctic Circle, the university was established in 1971 with a strong focus on mining and mineral processing, and has been one of the oldest research areas as a university. University is logistically located close to the largest mining operation in Sweden and Nordic countries, such as LKAB Kiruna iron ore mine or Boliden Aitik copper porphyry deposit. And as you can see, Luleå has very distinctive seasons. In winter, temperature can drop as low as -40 degrees, and in summertime, during recent years, temperature could rise up as high as 30 degrees, so around 70-degree difference between summer and winter. So let's begin with the motivation behind this talk. So traditional geometallurgical programs are often resource intensive, requiring extensive sampling, preparation, and lab work. However, exploration and pre-feasibility projects increasingly demand faster, cheaper, more efficient methods. The question that we are asking here is that can we obtain similar information without doing all the traditional testing or similar work that we were doing before? In this talk, I will focus mainly on comminution-related properties and present a few case studies that we could see the potential. So if I go a few steps back and look at the geomet concept, there in geometallurgical framework, the link between geology and process response lies in mineral and particle characteristics. We often think and work in terms of chemical assays. For example, in processing plant, we have grades and recovery that are based on the assays, but it's really the mineralogy and texture that determines metallurgical behavior. This concept that we see on the screen comes from Pertti Lamberg, former professor of geomet at LTU, which in his view and our view, the particle and minerals are connecting the geological model to the processing model. So minerals are the bridge, and that's where our attention should be. There are many approaches to geometallurgy, ranging from simple to more advanced one. The most comprehensive one is mineralogical and particle-based approach, where processing performance is directly linked to the mineralogy and or texture. We don't necessarily have to go through all the steps shown here, but the approach is most complete and essentially provides all the information needed for downstream processes. For example, we can extract mineral liberation or predict mineral liberation. It's clear that prerequisite for this approach and for most sound geometallurgical strategies is the proper ore characterization. I came across this cartoon during my PhD defense back in 2017, where Julie Hunt, my opponent, was presenting this, and I see that this is still relevant today. It illustrates a common issue we face in mining operation, the lack of common language among disciplines. What a geologist explains passionately is often only partially understood by metallurgists, and vice versa. Maybe partially is also a strong word. This communication barrier needs to be addressed if we want to maximize value from area exploration and geometallurgical studies. Much of the information needed for downstream process can in fact be extracted already from early exploration data and drill cores, which I go through shortly. So here's the outline of the today's talk. I will go through a few strategies for maximizing information gain. It follows the same order that we do normally during drilling campaign and sample preparation. This includes measurement while drilling, or MWD, while cutting measurements such as torque measurement during sawing drill cores, and core scanning technologies, non-destructive methods for characterization, and a few cases studies to show practical results and the potential of the techniques. When it comes to MWD system, they are an excellent first step equipment because they provide continuous drilling data, such as rate of penetration, torque, weight on bit, RPM, and pressure. These parameters correlate with rock hardness and comminution energy, meaning the drill leg itself becomes a measurement tool that gives rock variability before cores are analyzed. Even before core recovery, we can infer lithology and hardness. For example, we know that hard rocks show low rate of penetration with high torque and weight on bit. Softer and altered rocks show high rate of penetration and low torque, and fracture zones cause fluctuation reading. From these signals, we can generate hardness and structural maps to outline grindability domains and geological boundaries. Another opportunity lies in the core sawing process. Typically, cores are sawed along the axis, and half of the core is sent for chemical assays according to the certain protocols. Since this step is done anyway, why not use it to maximize the value and extract additional information? So in core sawing, by integrating sensors such as torque, we can collect real-time data on rock hardness during cutting. So this test rig, for example, records torque data, allowing us to estimate the work done during the cutting, which correlate to some extent with lithology and ultimately with rock hardness. It requires a bit of work and interpretation before being translated, for example, for ore hardness. It's very simple, yet very effective way to gather additional data from a process that we have to do anyway. So next step, we can look at the core scanning option and the types of information they provide. Many portable and mobile systems are now available on the market that allow rapid analysis of meter to kilometers of drill cores. Continuous XRF core scanning was one of the earliest technology developed for handling large core volumes. It basically measures elemental concentration along the core surface, typically from the magnesium to uranium, and with limited sensitivity for the lighter elements. The output data is continuous elemental logs or profile maps used for grade control, alteration indices, and confirming lithologies. It's fast, non-destructive, it requires calibration, surface roughness, and moisture can affect the results. A more advanced category of the core scannings include micro-XRF and LIP system. So micro-XRF can generate high-resolution elemental maps down to 20 micron, useful for studying textures. A resolution of 100 to 200 micron usually offers the best balance between the speed and the detail. It bridges the gap between the bulk scanning and microanalysis. It's excellent for visualizing vein, alteration zone, and overall texture. Then we have LIBS, laser-induced breakdown spectroscopy. It uses a focused laser pulses to create a microplasma, and the emitted light gives the sample's elemental composition. It produces fast elemental maps, including light elements such as lithium, boron, beryllium that XRF struggles with. The method scans point by point, requires careful calibration, and it has also little surface penetration. So it causes minor micro-scale surfaces damage, but is very negligible. In both microXRF and LIBS, there are also option and possibility to convert the elemental data into the false color mineral maps. Next, we have systems that directly measure mineralogy, the most common being hyperspectral scanners. The basic principle is very simple. They measure light reflected from a surface across many narrow wavelength bands to identify and map minerals based on their unique absorption features. The narrow wavelengths includes visible to near infrared, so it's usually used to identify iron oxide, hematite, goethite, and general oxidation or color variation. Then we have short-wave infrared, mostly for detecting hydroxyl-bearing minerals such as clays, micas, chlorite, amphiboles, carbonates, ideal for alteration mapping. Then we have long-wave infrared or thermal infrared, which captures shortcomings of the other wavelengths, mostly for silicates, carbonates, and it's useful for primarily rock-forming minerals that are not visible in the VNRI or the short wavelength infrared. The main challenge with hyperspectral imaging is its large volume of data and the need for expert processing and calibration. Another mineralogical method is Raman spectroscopy, usually applied as point or line mapping, sometimes integrated into the larger scanning machines. It identifies and confirms minerals, including polymorphs, calcite, aragonite, or we can also identify hematite versus magnetite, and carbon phases like a graphite, amorphous carbon, diamond, through vibrational spectra. So comparatively, Raman is slower than other sensors, but it's very precise. And beside that, we have the system that provide the chemical composition that we can post-process and convert these chemical compositions to mineralogy. Next, we have the multi-sensor core logger system, which is widely used in geotechnical projects or oil gas reservoir analysis. It's often complemented by RGB imaging for visual core documentation. More or less, all the previous systems include some sort of the RGB imaging. They are not very common for ore exploration, but to some degree can be used for diagnostic testing. So if we do a quick recap of the main system, we have the hyperspectral scanning. So it's best for alteration, mineral maps, and mineral chemistry proxies. It needs expertise and sometimes needed with infrared for silicates. We have the XRF, bulk XRF, best for fast grade elemental profile. Quantification is possible with the standards and needs roughness and moisture correction. Then we have micro XRF. It gives chemical assays, elemental maps, and mineralogy, can capture texture. It requires semi-flat surface. Then we have LIB system, basically covers the shortcomings of the XRF by including light elements that XRF struggles with. It requires good calibration for quantification. So if I move on to the next part, so among non-destructive methods, I mostly focus on those relevant for rock hardness and comminution. We have portable tools such as LIB rebound hardness tester and ultrasonic pulse velocity devices. So since the focus of this talk is mostly on comminution, so these portable systems are particularly very relevant. So they provide information on rock strengths such as UCS, uniaxial compressive strength, Young modulus, and in some cases we can correlate this information to grindability. Little about how lip hardness tester works. So lip consists of a spring-loaded impact body. So if I could show here, so it consists of impact body with the permanent magnet inside. So the impact body is launched by the spring energy that we have on the top against the sample surface, then rebounds back. So a permanent magnet that is inside the impact body induces a voltage while it's passing through the coil. And when the impact body rebounds, then also when it goes back through the coil, induces another voltage. So from these voltages, we can estimate the velocity of the impact and rebound. So the induced current then is proportional to this velocity, and we can use this to calculate the lip hardness. So it's a dimensionless properties is a ratio of the velocity of the rebound divided by the impact. Generally, in hard materials, the impact body rebounds faster, meaning that the higher rebound velocity relative to the impact velocity. Then we have UPV, which measures how fast ultrasonic or sound waves pulse travel through the material. So this system that we see here is mostly based on the P wave. So we can have also the S wave for the surface wave, but it's not very relevant for core characterization. And then the principle is based on the material itself, and the velocity that we have with the UPV is based on the material elastic properties, like plus the density, and if you have cracks or deformation inside the rocks. So in general, UPV correlates positively with the hardness, meaning that if we get higher UPV values, it usually indicates denser, stiffer, and more intact rock. And lower UPV usually correlates with the higher porosity, microcracks, and weaker bonding between the minerals, typically indicating softer material. So here I go through a few case studies. So the first case study is about whether we can estimate chemical assays directly from the surface of drill cores. This is interesting to see how close we can get by only analyzing the surface of the drill cores without sending the sample, for example, for external lab for pulverizing and doing XRF. So in this work, we use half of each drill core and then send the other half to the commercial laboratory for chemical analysis, and the preserved core we use for analyzing with micro XRF. And the samples here are mostly iron ore samples. So for each half core, we generated an X-ray intensity map. So this is analogous to BSE image that we get from SEM, meaning heavier elements appear brighter while lighter elements appear darker. We then created elemental maps we see in the middle. Finally, we generated mineral map based on the spectral data for each point to visualize the mineral distribution. So this stage for this part of the work wasn't necessarily, but this was useful in other examples that I will present later. To be able to get estimation of the chemical assay from the elemental map, we use aggregated spectra of all the regions measured on the surface. At the first stage, we calibrated the micro XRF by analyzing the same powder samples that were sent to the commercial lab. The graphs you see for iron, sulfur, and phosphorus show the results after calibration. So overall, we see very good correlation between bulk micro XRF analysis on powder that we did and the results from the commercial lab. So we are mostly focusing here on iron, sulfur, and phosphorus, which was relevant for iron ore processing. So this graph shows a comparison between chemical assays and micro-XRF analysis of the drill core samples for iron, sulfur, and phosphorus. Although the correlation is generally good, it is clearly not the same for all elements. Obviously, the differences arise because powder sample represents a homogenized volume, whereas the drill core scan reflects the natural heterogeneity of the rock surface. So the best correlation observed in the sample with the homogeneous. So when we have the parity line, so the points that are close to the parity line generally belongs to fine grain homogeneous texture compared to the one that are far away, which usually belong to the coarse grain heterogeneous textures. And one other source of the deviation could be that we analyze a smaller area of the core compared to the other half core that was sent for chemical assays. So next case study is on Lieb's hardness. So here we try to study nickel, copper PGE, and iron ore samples. The main data used in this study were core logging information by geologists, Lieb hardness that we did on the surface, UCS data that we did with the point load test, and the bond work index that we used GCT test. So the idea was if you could estimate correlation or find correlation between Lieb hardness and UCS or bond work index. So for nickel copper PGE on the left, we can see the correlation between Lieb hardness and point load index, showing the distinct population for different rock types. So I focus only on two extreme cases. So typically we have breccia, brown or reddish points that we have in this region is associated with the lower Lieb values and basically softer material, while gabbro blue points that we have on the right side shows highest hardness values. So this shows that the behavior and correlation between the Lieb and point load indices varies between the rock types. So we cannot conclude that there is a linear relationship if we put all together. Here we have similar graph for iron ore case. On the right, we see the correlation between the Lieb hardness on the y-axis and the point load index, UCS, on the x-axis. And we see this almost linear correlation. And then on the left side, we have the correlation between the GCT work index and the Lieb hardness. The graph on the left should be interpreted cautiously as the number of the data point is limited and correlation may only be applicable to a specific rock type that was tested here. So the rock type here was mostly massive iron ore. Here is another case study done on the zinc-lead deposit by Fraunhofer Chalmers Research Center in Sweden. So the main data used in this study were core logging information, rebound hardness by Schmidt-Hammer. So basically Schmidt-Hammer is also rebound hardness test, similar to Equitip, and P-wave data and core sign torque that I showed earlier. And they use supervised machine learning, random forest method for correlating the data. The idea was if we could predict torque, P-wave velocity, and hardness from XRF data. So here on the left graph, we can see distinctive responses of rock types in P-wave velocity, so at least two. So limestone shows very distinctively lower P-wave velocity compared to quartzite and other rocks. And if you look at the Schmidt-Hammer hardness on the right side, so this is more a spread. And we can see for limestone, this is a more narrower. So in these graphs, we plotted observed versus predicted values based on the XRF assays. assays. So the prediction model is based on the training data of XRF and the responses such as torque, P, wave velocity, and hardness. The data points are also color-coded based on the rock types. So if you compare different graphs for predicted torque based on the XRF assays and P wave velocity and Schmidt-Hammer, the best correlation we see is with the core sawing torque. The next best is a P wave velocity, and the last one is a Schmidt-Hammer. Then we have another case study, and this one focuses on ore texture and its correlation to hardness. And we are exploring whether we can correlate leaf values to different textural patterns in the drill course. We have used core logging information, mineral maps from the micro-XRF scanning, and converting those to using the omics to convert those to minerals, lip hardness, and unsupervised machine learning. And the drill cores are iron ore drill cores. So we have started by generating X-ray intensity maps that we see in the middle, as well as mineral maps from the elemental data. In the sample, we have a distinctive region rich in sulfides. We see here with the yellow color. And then we have the region with the amphibole, large amount of amphibole and feldspar on the left. First, we converted all the mineral map images to gray level images that we see here in the middle part. Then we did the image processing and filtering and defined patches of 1 centimeter to 1 centimeter. So the choice of patch size is kind of tentative, but as a rule of thumb, it should be large enough to preserve a spatial textural information, yet not too large to mix it too much with the textural variation. So after a few steps of filtering and processing, the patches that they were roughly around 50,000 were eventually classified into 7 clusters that we see here. Some clusters, such as number 7, shows very clear and consistent classification, while others we can see there is a larger internal variation. Here we can see the original mineral maps are overlaid with the clustering and texture classification results, with each cluster shown in different color. So in figure A, a fine-grained, massive, and homogeneous texture is entirely classified as a cluster 5. And in figure B, we have heterogeneous medium to coarse-grained massive texture. It's mostly falling into cluster 1 and cluster 7. Then we have lip hardness measurement that were then mapped on the samples. So we can see how they correlate with each textural class. We could identify 3 main hardness domains. So hard domain with values above 700, and medium domain between 600 to 700, and the soft domain less than 600. So at the top, yellow, more homogeneous texture pattern is classified as single cluster. So the hardness value are more consistent and average above 700, so indicating this is a hard rock. And at the bottom, we see this heterogeneous sample with a larger value in the lips hardness. Perhaps the most important takeaway from this webinar is this point. It's very easy to draw conclusion from empirical relations, but one should always be cautious about their pitfalls. A good example comes from the statistical analysis comparing the number of the stork breeding pairs we see on the x-axis and human birth rate on the y-axis. So one might think that the storks deliver babies, so it could be a hypothesis. And then empirical relationship shows the trend, and the p-value for this relationship is actually very low, so suggesting that there is a strong correlation. So there is actually publication in the Journal of Teaching and Statistics from 2001. This discussing this case. So to wrap up what I presented here, we have many portable instruments available nowadays for acquiring large data sets ranging from chemical assay to mineralogy or even texture. With this massive amount of data, it is possible to generate digital cores and correlate processing parameters to lithologies or in finer details to different textural clusters. The important key question is what data is relevant to you or your case to maximize information gain at earlier stage from drill cores. But the main challenge is still and now to make sense of this large data set and being cautious with empirical relationships. And that was the last slide.
Great. Thank you, Mehdi, for that very enlightening presentation. So I'm going to now open up the floor for questions, for Q&A. If you have a question, please post it in the Q&A. And while we get some questions, maybe I think I'll start with one. So you've mentioned a lot of techniques and you've given us a whirlwind tour of what's available. What do you reckon is the uptake of these in the actual mining industry as opposed to just a research tool?
I think it comes to mind the throughput. So in the research, we can afford to go, let's say, high detail, a few samples, but most of the mining industries, at least the larger ones, they want a fast turnaround, something that can analyze kilometers of the drill cores and with the least expertise to actually make sense of data. That's a nowadays trend because it's building expertise, for example, hyperspectral imaging. Not everyone can generate the high quality information data.
Okay. And in terms of these techniques, I mean, maybe this is a question that I'm interested in. The ultrasonic P wave, it seems like it's got a lot of potential, that technique, but from what I recall, there's a lot of information like geophysics type stuff that you need to actually be able to input to actually get something out that means something. Can you go through what we actually need to run this technique?
Simplest way is to only use or look at the velocities. So that's a simple basic principle. So we can correlate velocities to hardness of material, how intact the, for example, core is. The problem with the P wave and ultrasonic is that it's not very easy to conclude something from the internal structure. Then we have done some work. We were looking at the shape of the waves. So we see, for example, foliation in the drill cores, they generate certain type of wave shapes, but it's really, really hard to interpret it in a way that you could correlate it with the texture of the sample. For, let's say, simple cases, we can only take velocity and it correlates well with the different lithologies. But if you want to go to the detail, then probably is not the best way to go. But for the larger scale, rough information that we can get earlier stage is very good method.
So for something where you've got one lithology but differences in porosity, would you be able to use it?
I would assume so, because it's very sensitive to porosities and the cracks.
Okay. All right. So we're starting to get some questions. We've got one from Andre van der Westhuizen. He says, hi, Mehdi, you mentioned a number of non-destructive techniques. Considering cost and resources, which top 2 or 3 would you recommend as techniques that could be quickly implemented?
So this is generally correct as how much you pay for you get. So bulk scanning probably is the cheapest method, and it's very fast. But the information that we get is mostly elemental profile through the depths. The more advanced method we go, the trickier and the slower and more complicated it gets. So it means that we need some type of expertise to comprehend the data and interpret and get something useful out of it. So if you mean non-destructive technique like a testing, like a leap hardness and UPV, I would say leap hardness is a very good way of finding proxies. But also I know that it's very sensitive to calibration and how you do the test. For example, if you do leap hardness on certain diameter drill cores, you cannot compare it with the data that was done on the different diameter drill cores. So the way that you do the work, it should be consistent, systematic, and know the error and pitfalls of the test that you're doing.
Okay. We've got a question from Michelo, and I think this relates to the P-wave stuff. They've asked, can this be applicable not only in drill core, but also in drilling dust collected each meter downward for analysis of mining applications? Maybe Michelo can also just clarify this question.
If it's about using on the powder, it would be very unlikely because it's very sensitive to the porosity and the surfaces.
Okay. And then we've had a question from Fatimata Diallo. What are the chemical elements used to correlate with hardness?
That's the thing. So we use chemical elements, but it's not actually the chemical elements that correlate with the hardness. It's the mineralogy and texture that correlates. So we can find, for example, correlation between iron and certain hardness region, but this basically translates to what kind of mineralogy this iron has or was bringing that correlates with that. So simple case, if we see high iron, probably indicate you have a lot of hematite, then this could be correlated to hematite, that it was kind of presenting itself as an iron content. That's why it's a bit tricky to build this empirical relationship, especially based on the elemental compositions. So we see the patterns here and there, but if, for example, mineralogy changes, not the chemical composition, then there would be little dangerous.
All right. Desh Chetty's given us a question. Hi, Mehdi, great to hear your presentation. With all of these techniques, how do you make the link to energy requirements for comminution plants and handling ore texture variability, given the differences of scales of observation versus mined material?
Yeah, this is very tricky. So, and maybe first, nice to hear from Desh. It's been a long time that I haven't seen her. Yeah, so that the work that we did was mostly on the research part, so to classify the texture and to correlate this to the, let's say, larger operation for the work index. I would say we went to really fine detail. We went to the range of like a 1 centimeter to 1 centimeter patches. So probably for the larger operation, we should go up to a bit larger scale. So first, micro scale mapping with the methods that exist that we can do on the surface or on the exposures, then go on certain region to more detail, and then correlate from this high resolution data to the larger images that we have. Maybe simpler way would be to somehow find larger classification of the texture that you have in your lithologies and in the ore. The main problem I see with this is that we are only looking here at the minerals. So we are not looking at the cracks or micro cracks or effects that the rocks has. And we know that that has also a really large effect on the grinding and comminution. So what we are kind of assuming here is that all those defects also reflected with the mineralogy. For example, if we see alteration, this is also carried by this mineralogical information that we have. And that's a little tricky. So I would say it's not very straightforward.
Okay. Kalen Govender has also given us a question. He has said, it's quite a long question, so I'm going to try and go through it. Have you explored the use of machine learning to relate the available large data sets? In previous roles that Kalen's explored the use of ecotip to predict similar drop wake index in UCS with limited success across iron ore, platinum, and kimberlite. He believes this was largely related to the inherent noise from the Lieb methods. The best success they've had has mostly come from relating spectral data to predict hardness and recovery larger in copper and platinum. What are your thoughts on FDRR and other IR methods, and do these methods fit into the basket of rapid data acquisition?
So I agree with him or her, I don't know.
Him.
Him, yeah, I agree with him. So Lieb hardness is very tricky. You need to do a lot of test work before you can make sense of data. The spacing that you have, the amount of sample that you basically do the test, and consistency is the key. And I also agree that textural and mineralogy would be much easier and makes more sense to correlate to the hardness. This is a case-by-case question, because let's say you want to use IR or thermal infrared. So this depends on what kind of mineralogy you are missing in the normal visible range or other range that you cannot basically identify. Since recently we are working a lot with the micro XRF and chemical data, it's from what I did and what we understood, it's really easy and straightforward to correlate data from macro XRF generated mineral maps to this kind of indices. The only limitation is the lighter elements, which usually, if you are not going for the lithium, boron, or beryllium, it's not the issue. So above, let's say, sodium, we should be able to detect everything.
So we've had a question from Christopher Coburn. What method would be best, both cost and time effective, to collect quantitative textual data such as average particle size or particle size distributions?
Average particle size or grain size? That's the question.
He's written particle size, but maybe we do mean grain size. Let's assume it's grain size.
Yeah, so I assume that's the grain size. That's a little tricky, because probably we will not be able to see the boundaries between the grains. So we'll see the whole bunch that they are together as one large area. If this is scattered or there are inclusion or single grains within, yes, of course. But in the normal XRF, I assume that's not possible. So it's not very easy to see the grain size similar to what we do in SEM.
Then we've got one from James Wilson. Can you elaborate on how these techniques will lead to cost savings in feasibility test work, bearing in mind you will in any case need to perform a range of full direct test work on the ore materials for a feasibility study?
So if you start from beginning, so there are stuff that we have to do anyway, right? So we do the drilling. This drilling could be for campaign in exploration, or could be drilling for the blasting explosives. So in both of them, there are rigs that we can extract information. Then we have the core sawing. So that's also a possibility. So because we have to saw the core anyway, if you want to do the chemical assays for the deposit or the resource estimate. So we can also get information. So up to this point, we are basically doing whatever we were doing normally. So from this point forward is the question that how we can actually save money. So because if we do something extra, it costs money. But what we can do is, for example, in the core scanning, we already can screen a lot of information and then handpick certain areas or certain lithologies that we know that is relevant, instead of going through everything and then rely on maybe core logging information. I had the experience of we had some customer or let's say partner that sent us the core logging information about the drill cores. And then we had the list of the minerals that they were in the cores. And then we did the macro XRF, we did element to mineral conversion with the omics. Then we realized that many minerals that they had in the core logging, they are not actually in the cores, at least according to the data that we were seeing. But they were very similar to the minerals that they were claiming that they were there. So based on the core logging information, they decided on some test work or some regions, but based on the core scanning that we did, there were some other minerals present that basically indicated some other information that they were missing. So it's we think that we are saving money by not doing some type of work, but I think the information that you get in the end is very helpful on decision making, and also narrow it down where in the, for example, deposit you need to look closely, where you should have the focus on the test work and how much variation you have.
All right. Staying with the chemistry, we have another question from Fatimata Diallo, which is about the element to mineral conversion. And she's asked, have you been able to practically and routinely convert chemical data from portable XRF to mineralogy for large samples, especially for mining companies?
It depends on the quality of data. So we are talking about the portable XRF. And so if it's, let's say, on the same ore all the time, and the method is systematic, and there is a calibration to correct all the portable XRF data, and we have limited mineralogy that we want to calculate, then it should be possible, yes. So actually, we have a course at university about geometallurgy, and part of that is actually how to do the element to mineral conversion, how to calculate a stepwise different minerals based on the chemical assays. So in, I would say 5-6 minerals, 5-6 assays that reliably can be measured, yes, it's possible. But if you have 15, 20, 50 minerals and then 10, 20 assays that maybe they are good, probably no.
Okay. And we've just got another comment from Kalen, who's mentioned looking at the AXT Labs eCore Lib sensor, that he's seen some fantastic textual data produced there. All right. I think we got through most of our questions. There was another one. Can we analyze different structures with Lieb rebound hardness?
That's a good question. So what we know is that Lieb is there is a certain area of effect than when we hit the sample. So I heard that is around like a 2 centimeter of the depth and surrounding. So if there are something beneath the surface or structurally different, then it will be reflected on the Lieb's reading. But the difficulty would be to say if it's coming from this a structural difference or it's because of the mineralogical difference, if you only have access to see the surface of the material. But by theory, yes, it should be possible to do that. But the range of the data that we get from the Liebs are 1 or 2 centimeter depths of the place that we test.
And then Baldwin Sincumber has asked, I think he's asking about the Lieb and how it relates to the HIT, the hardness index tester.
HIT is similar for the A and B value, right? For the drop weight. Okay. No, it's not similar. So that's the thing. So I've seen publication that they correlated lip hardness to A and B and drop weight indices, but this should be verified case by case. I don't think there is a universal correlation through all the lithologies or everywhere. So this is a part that I'd always try to be cautious to draw empirical conclusion between one method to another, because we need to look at how method works. So if we look at the hit is the impact, and then we break the material based on the impact. And the rebound is basically the stiffness and rebound of this impact body that gets back from the sample. So I don't see them to be exactly the same way characterizing the rock. So they might refer to same thing as a hardness, but I don't think this would be general correlation through all the samples.
Perhaps I can just add, the hit test is also very much about a particle test. It's a destructive test. You break the particles, you measure the particle size distribution. When you're done, the lead is something that's non-destructive. That drill core is still available for any textural analyses you want to do afterwards, and it's been preserved.
Exactly.
All right. I think we are about done. So I'm going to say thank you very much, Mehdi, for your presentation, and also for the audience who've engaged with us and given us a good discussion. It's such an exciting space, this. Maybe just a last question. 5 years' time, what do you reckon will be the most hottest topic of these measurements that we're talking about?
Everywhere is AI. So,
okay.
So yeah, it should be AI. So now it advances so fast. So we are now talking about the digital cores, digital twins. I know there was some challenges to translate the information that you have digitally from, let's say, deposit to the process, but I think that would be the future.
Great, thank you.